Bam! Mr. Tarot. In this video, we are going to learn how the first derivative will allow us to find open intervals in a function where the function, we're going to identify where the function is increasing and where the function is decreasing and where it is constant. We're also going to learn how the first derivative will allow us to identify those relative max and those relative mins, whether it's at a smooth bend or at a sharp bend. We're going to finish up after we get a lot of notes about the definitions and theorems and whatnot, vocabulary. We're going to go through 3 algebraic examples and then a 4th example where we just look at a function, a graphical function, basically a picture. I'll draw a picture of a function. We'll come up with a sketch of what the first derivative could look like, and again, try and identify, allow it to help us identify those increasing, decreasing, and constant intervals and relative maxes and mins. So increasing and decreasing functions and the first derivative test. When a graph is read left to right, you want to read these kind of like most languages, I think. You read left to right, so you kind of read it like a book, I like to say. A graph is increasing when it rises to the right. Or, in more mathy language, a function f is increasing on an interval if, for any two numbers, x sub 1 and x sub 2, in the interval, if x sub 1 is less than x sub 2, this implies that f of x sub 1 is less than f of x sub 2. What does that say? It says if you have a bigger x, you have a bigger y. So it goes up to the right. A graph is decreasing when it falls to the right, and again, that's sort of a very formal math definition. A function f is decreasing on an interval if for any two numbers x sub 1 and x sub 2 in the interval x sub 1 is less than x sub 2 implies that f of x sub 1 is greater than f of x sub 2. So, again, what does that say? I write all these notes and these properties and whatnot from the textbooks because a lot of us have trouble reading them and trying to decipher them for you. So what does it say? X sub 2 is greater than x sub 1. So if you have a bigger x and you put that into the function, you actually get a smaller y value. You know, f of x, it's function notation for basically y, or the dependent variable. A test for increasing and decreasing functions. Let f be a function that is continuous on the closed interval of a to b and differentiable on the open interval of a to b. If f prime of x, or the derivative of f of x, is greater than 0 for all x's in that closed interval, then f is increasing on that closed interval. If the first derivative is less than 0 or negative, then it is decreasing, the function is decreasing along that interval. And if the first derivative is equal to 0, well, then you have a constant. On the next page here, we're going to take a look at steps for finding these open intervals, and I'm going to give you a graphical display, kind of just some crazy graph I've made up, and show you how these intervals look, you know, increasing, decreasing constants, and have some sharp bends in it as well, and special cases we'll have to look out for as we do our homework. Steps for finding open intervals of increasing and decreasing. Step 1. Well, this is all about the first derivative, so you're going to have to find that first. Step 2, solve for set f of x, or the derivative of f of x equal to 0, and then set it equal to, find out if there's any values where it can be undefined, like maybe you have a rational function and there's an x in the denominator. If that denominator can be equal to 0, what are those values making the function undefined? Or trig functions, you know, like sine of theta is y over r. So, well, actually, that's a bad example because sine's never actually, it's defined for all values within the domain of all real numbers. Maybe like tangent. Tangent of theta is y over x. So what rotation would give you an x value that's equal to 0, thus making your tangent function undefined? So find what, again, makes your derivative equal to 0 or undefined, and those are going to be your critical values in your open interval. And you're going to use those critical values to determine or set up your test intervals. Basically taking your number line from negative infinity to positive infinity, or whatever domain is set up in the problem, and breaking up into sections based on these critical values. Then you're going to plug in one value from each of those intervals into your derivative, and if you get a positive answer, then the function is increasing in that interval. If you get a negative answer, it's decreasing. And if it ends up being 0, well, it's kind of, you know, you set the first derivative equal to 0 to find your critical values, unless it ends up just being a constant function like a horizontal line, which is kind of a special case. Strictly monotonic functions only increase or decrease in the entire interval. So let's say like you maybe just have a function that has a degree of 3, like a regular polynomial with a degree of 3, where it comes up and it does a little bit of a bend in the middle, but then just continues to increase. That would be a monotonic function. It kind of, you know, the slope's not constant, but it never stops, say, increasing within its domain or within whatever interval you're interested in. Over here, I've got a visual representation of what I've tried to put in these steps. I got some kind of crazy squiggly line. I just made that up. I can't imagine what the function would look like that would make something like this, except I can pretty much guarantee it'd be a piecewise function. And with multiple pieces, we have a function that is increasing in this interval, and that first derivative, because the function is rising to the right, would be positive. And then my graph levels off. So the first derivative at some point, at least the way I've drawn it, maybe it comes out to be 0. So the function is increasing, it levels off and becomes horizontal, maybe even just for one point on that function, if you will, and then it starts to rise again. So when you find a critical value, such as when your derivative is undefined, or especially at 0, it doesn't mean that your graph is going to sort of, stop rising and start falling. It can level off and then continue up again. Then we have another interval where the first derivative, as I have drawn it, would be positive. We have, again, another critical value where the first derivative is equal to 0. And this time I do have the graph starting to fall. So this is a preview of what's on the next screen. I'll give you the formal language called the first derivative test. But if your first derivative goes from being positive to negative, that means that it stopped rising and started to fall. Well then, at that point, somewhere between that rise and fall, you've got a relative maximum. And we're falling with a negative first derivative, and then it switches from a negative first derivative to a positive, and that means that you've sort of bottomed out. You're going to find a relative minimum. Now, your relative max and mins don't have to happen at a smooth continuous point. It can show up at a sharp bend, which is why we need to find out where the first derivative is equal to 0 and where it's undefined. It's not necessarily going to be a vertical asymptote like maybe you would have in a rational function. Maybe it's an absolute value function. So with that sharp bend, if the first derivative goes from being positive to negative, that is a critical value. It would have help you set up your intervals, and in this case, the way it's drawn, that would be another relative maximum. And then the graph, the original function is a rational function and it's undefined at some value, so it just shoots down to negative infinity, and this value here of whatever, c, makes the function, the original function, undefined. So sometimes we do need to go back and make sure that the function itself is not undefined somewhere. Like at this point, my first derivative would be undefined. But if my function is continuous there, well then I'll have a sharp bend, like an absolute value function. But sometimes when when the first derivative is also again undefined, that is a possibility that not only is the first derivative undefined, but the actual original function is undefined as well. That could be in the form of a hole, or how I have it drawn in this diagram, a vertical asymptote. So that would be a discontinuity right there, and you're not going to have, you're not going to have a relative max or min at a point of discontinuity, even if it's a hole. And maybe the y value of that hole is 4. You would come infinitely close from the bottom and infinitely close from the top, and maybe you're coming up to 3.9, 3.99, 3.9999, 3.999999. But as soon as you pick a value, I can get a little bit closer. So there's not going to be a relative maximum coming to a hole, just like when we talked about finding max and mins with open and closed intervals. You can't have an open dot be a relative max or an absolute max or min for that matter if it was going the other direction. And then of course we have another positive first derivative because the graph is rising to the right, and then I just drew an area here where the slope of the original function is horizontal. That would be a first derivative value of 0, and it's a constant value. For some reason it just becomes horizontal over there. So that's a visual representation of how you would, the importance of these critical values helping you to set up these intervals and find those increasing and decreasing intervals along the function. And I gave you a preview of the first derivative test. So let's get to it right now with some official notes. Alrighty then. to put into formal introduction what I had in that previous diagram, the first derivative tests. Let C be a critical number of a function. Again, first derivative equal to 0 or undefined. Critical number of the function f that is continuous on an open interval I containing C. If the function f is differentiable on the interval except possibly at C, like those sharp bends I was talking about, then f of C can be classified as the following, or as follows. If the first derivative f changes from negative to positive, then at C, then the function f has a relative minimum at C, f of C. If it changes from positive to negative, rising and then falling, then you have a relative maximum at C, f of C. And then, like at the very beginning of my diagram where it rose, leveled off, and rose again, if the first derivative does not change sign on both sides of C, then f of C is not a relative max, nor is it a min. Woo! Alright, all those fancy notes are done. Let's get to some examples. Remember, 3 algebraic examples and 1 graphical one. Let's get critical, critical. We got f of x is equal to 1/3 x cubed minus 1/2 x squared minus 6x plus 4. I want to find all the critical values so I can use them to find the intervals where the function is increasing, decreasing. Okay, I'm not going to start off with a really hard example in the beginning, so we need our first derivative. So f prime, or the derivative of f, this is just a very basic polynomial. Doesn't look like it, but it will once I get finished taking the derivative. So we've got 3 times 1/3, which is 1, so we have x squared. We've got, bring the 2 down, and we get minus 1x, and then negative 6x, the derivative of negative 6x is simply negative 6, and that's a constant, so the derivative of a constant is 0. Our critical numbers are where the first derivative is equal to 0 or undefined, so I want to set this equal to 0. So where is, again, f prime equal to 0? Well, that's going to be x minus, or x squared minus x minus 6 is equal to 0. This one's very easily factored. We have x minus 3 times x plus 3, excuse me, easily factored, I'm making a mistake, plus 2. That means we have critical values of x equals 3 and negative 2. When we set up those intervals, make sure you go from low to high, or from negative infinity to positive infinity, or whatever your interval is defined in your problem. So again, where our first derivative is equal to 0 is not the only possible critical values. I want to find out where f prime is equal to undefined. This is a parabola opening up. It's a polynomial. It's smooth and continuous everywhere in its domain, or everywhere from negative infinity to positive infinity. So the solution to where is f prime equal to being undefined, there is no solution. So our intervals are from negative infinity to negative 2, and from, now we're going to go from negative 2 to 3, and then finally from 3 to positive infinity. And we're looking, of course, for the signs of our first derivative. So our first derivative, now I only have to test one value within each of these intervals. So let's say like negative 3. Well, negative 3 squared is what, 9? And 9 minus negative 3 is plus, so 9 plus 3 is 12. And then 12 minus 6 is, well, that's a positive number. So from the interval from negative infinity to negative 2, our function is increasing. Now I have another interval from negative 2 to positive 3. Okay, let's try a test interval value of 0. If I plug in 0, I get 0 squared is 0 minus 6. Negative 6 is, just said it, it's negative. So we have a function which is, again, increasing, decreasing. Now this isn't automatically going to be increasing again. You can, the graph can level off at that critical value of 3 and then continue to fall. So let's make sure we check it. 4. Okay, 4 squared is 16. 16 minus 4 is 12. And 12 minus 6 is 6. I don't really care that I know that it's 6. All I really care about it again is that I know it's positive. So the graph is once again increasing. All right. Well, use the first derivative test to determine all relative max or min. So in other words, is there a place where the graph bottoms out, setting up a relative min? And if that's the lowest y value in the entire function, it's actually an absolute min, but relative min have less criteria, so we start with calling them that. And then we're going to look, and we're going to test that at -2, and then test 3, so let's see what happens. Okay, so our critical values, -2, 3. Our function stopped increasing and started to decrease at -2. So we went from being positive, as far as our first derivative, went to being positive to being negative. So it looks like we have a positive, negative, looks like we have a relative maximum at the x value of 2. So we have a relative max at at -2, comma, f of -2. Now you're going to have to take that -2, remember to plug it back into the original function, not your first derivative, like you were doing for your test intervals. And when you plug that -2 back into this function, right off the top of my head, you're going to get a y value of 11.3. So we have a relative max at -2, 11.3. Now, at our other critical value at 3, our f prime again, I'm just summarizing this again, I don't know why, I could just point to it, but we go from negative to positive, which means that we were falling and started to rise again, so we have a relative min at -2, excuse me, thinking about the other number, 3, f of 3, and when you take that value of 3, plug it back into the original function, right off the top of my head, we have a relative minimum at 3, comma, -9.5. And if you were to put this into your calculator, we have a graph that's increasing from -infinity up until you get to a value of 2. This will be a very rough sketch, but -2, excuse me, 11.3. The graph is going to fall. It's going to fall until you get to 3, comma, -9.5. And then since that was our last critical value, the graph is going to start to increase and go off to positive infinity. If you remember graphing polynomials, and we're getting back to this, in pre-calculus you graphed polynomial functions of higher order degrees, and we talked about end behavior, and we talked about x and y intercepts. What we missed in pre-calculus was the ability to find those relative max and mins and actually know how high the graph rose before it started to fall again. So we're actually going to go back to that topic in pre-calculus of graphing higher order polynomials. That being said, we have a third degree polynomial with a positive leading coefficient, and we did talk about last year end behavior of these functions going down to the left and up to the right, and indeed we can see that with this function being verified by our first derivative. Next example! Y equals 2x squared over x squared minus 4, a quotient. So a little bit more work to find the derivative. Same thing though, find the critical values, find the intervals of increasing and decreasing. Use the first derivative test to find the relative max and mins. And I'll finish with the sketch of this graph as well. Do a little better job of it than the last one. So we need to find the derivative of this quotient. That means we need the quotient rule, and that means that we're going to take the denominator, which is x squared minus 4, multiply it by the derivative of the numerator, which is going to be 4x. Using lots of parentheses because I have multiple terms here now and I want to make sure my distributive, all my distributive properties work and I have everything, of course, correct. Minus the numerator, which is going to be 2x squared, times the derivative of the denominator, which that's going to be 0, so we just have 2x. That's only one term, so kind of didn't really need the parentheses there, over the denominator squared. Okay, let's clean this up a little bit. We can apply the, we are finding the derivative. It'd be nice if my notation was correct. Okay, so my derivative of y. So we're going to take 4x and multiply it through the parentheses and get 4x cubed minus 16x. Negative 2x squared times 2x is going to be negative 4x cubed. Again, over that denominator of x squared minus 4 squared. Of course, 4x cubed minus 4x cubed is going to cancel out. And our derivative, again, is equal to, get it down here so we can kind of see it more clearly, negative 16x over x squared minus 4 squared. Just make sure I didn't do something silly. Good. Checks out. Okay, our critical values. Well, that's where the first derivative is equal to 0 or undefined. And now we have a rational function. If the numerator is equal to 0, the function is equal to 0. If the denominator is equal to 0, well, then it's undefined. So our first derivative is equal to 0. Well, where's that at? Well, negative 16x is equal to 0, and that means that our solution after dividing both sides by negative 16 is x equals 0. So that is definitely a critical number we'll use to set up our intervals. Another thing we need to solve for is where's the first derivative undefined? Well, f prime is equal to being undefined or is undefined where the denominator is equal to 0. And that is x squared minus 4 is equal to 0. Add 4 to both sides. We get x squared is equal to 4. And that means that the first derivative is undefined at x values of positive and negative 2. Now these might be sharp bends in the graph. Or it might be where the graph itself, the original function, is undefined. If the original function is defined at 2 and negative 2, and it's just the first derivative that's undefined, then we're looking at probably sharp bends here, and we will have relative, possibly some relative maxes or mins at these points. We won't know that until we finish the whole problem, but we're not going to have relative mins and max if this is where the original function is discontinuous. And indeed, I hope you didn't think I forgot, this denominator has the function or the polynomial of x squared minus 4 just like the original one. So the original function is undefined at 2 and negative 2. So these are actually discontinuities and we're not going to have a relative min or max there. But it's still going to set up our still going to help to set up our test intervals. So the domain of this function is basically all real numbers except that x cannot equal 2 and negative 2. All this pre-calculus, and actually Algebra 2 coming back, of graphing these rational functions in calculus. Okay, our test intervals are going to be from negative infinity to negative 2, from negative 2 to 0, put these in sequence, and then from 0 to positive 2, and then from 2 to infinity. Excuse me for the pause there. And we're looking for signs of our derivative, our first derivative. So if I plug negative 3 in here, well, negative 3 plugged in for x, negative 3 times negative 16 is going to be positive 48. And the denominator I know is going to be positive because the entire expression is being squared. So even if x squared minus 4 comes out to be negative, it's going to become positive because of that power of 2. So I plug in a negative, it becomes positive, it's over positive, so the first derivative is going to be positive, or the function is going to be increasing on that interval. Now we skip over this critical value and go to our next interval from negative 2 to 0, so let's try negative 1. Negative 16 times negative 1 is positive, again in the numerator. The denominator is going to be positive guaranteed, so positive over positive means our first derivative is going to be positive, which again means our function is going to be increasing. And then moving over to our interval of 0 to 2, if I plug in 1, 16 times 1 is positive, excuse me, try that again. Negative 16 times 1 is negative over positive value, so our first derivative is going to be negative. That means it's going to be decreasing. And it's going to, if we plug in a value of 3, it's going to be negative again and going to be decreasing. So we have, here it's, you know, again, we have three critical values, but the first derivative shows that the function is increasing almost everywhere. There's only one place where the function actually changes directions and creates what is going to be a relative maximum, because we're going from positive first derivative to a negative first derivative, where it's going to stop rising and start to fall. And the function is defined at the x value of 0. If it was undefined, if the original function was undefined at 0, again, it wouldn't be a relative max or min, because you can't have a relative max or min when you're approaching a whole or a vertical asymptote. So, our first derivative test says that we have a relative, let's see again, positive to negative, rise to fall, so relative max at 0, f of 0, which is 0. Go to my original function, I plug in 0 for x, and we're going to have 0 over 0 minus 4, and 0 over anything other than another 0 is equal to 0. So we have a relative maximum at 0. I'm going to pause the video, erase a little piece of this board, and we'll just see what this function looks like to verify everything we observed in our first derivative test. Here we go. We have our vertical asymptotes at x equals -2 and +2. We have a relative maximum at 0, 0 that our first derivative test showed us. And just to point a couple of things out again, rational function, where the rational function is equal to 0 in the denominator, it's undefined. Now, if that 0 in the denominator can be factored, or excuse me, not factored, but canceled with the numerator, like maybe we have an x minus 2 and an x minus 2 up here, if that 0 in the denominator can be canceled out of the numerator, remember that's where the holes are, this x plus 2 and x minus 2 does not factor away. We have those vertical asymptotes because of that. And we're going to be talking about infinite limits soon, or the limits as x approaches negative infinity and positive infinity, which is very reminiscent of looking for your horizontal asymptotes in pre-calculus. Our numerator and denominator both have a degree, they're polynomials, and they both have a degree of 2. And when your degrees of your numerator and denominator polynomials are equal, you have a horizontal asymptote where the leading coefficients are. So it's y equals 2 over 1, and so we have a horizontal asymptote at y equals 2. And here we're increasing as we approach that first value, the critical value of -2, and we're increasing again. We're coming from the opposite sort of end instead of positive infinity, negative infinity, but the graph is still rising. And again, that's 0, 0, so we have a first derivative that goes from being positive to being negative. We get to the asymptote, and it continues to fall. So, where's my remote? Let's get that next example. I might be able to want to see that again. Y is equal to x minus 5 cosine x. So a little trig in there. Same steps. Find the derivative, find the critical values, set up the intervals, find out where the function is increasing, decreasing. This time on an interval of 0 to 2 pi. And then use that information to identify any relative max or mins. Okay, so that means we need the derivative. So y prime, the derivative of x is equal to 1. Minus 5 times the derivative of cosine. Now cosine, the derivative of cosine is negative sine. Negative sine. So we're going to come back here and change that to a positive. Excellent. So we got y prime is equal to 1 plus 5 sine of x. Where are the critical values? Well, there where the derivative is equal to 0. So let's set this up. We've got 1 plus 5 sine of x is equal to 0. We're going to subtract 1 from both sides and get 5 sine x is equal to -1. We're going to divide both sides by 5 and get the sine of x is equal to -1/5. And now we need to get the sine function away from the x. So x is equal to the inverse sine of -1/5. Now I hope you remember from last year in pre-calculus, and we've done a little bit of trig already this year in calculus, that you cannot do the inverse sine. Like, if you look at the original sine function and think about what it looked like, its range was from -1 to +1. And what do you put into a trig function? An angle measure. What do you get out? The sides of a triangle, or the ratio of y over r. The inverse trig function, therefore, you're putting in the y over r and you're looking for the angle measure to come out. Well, if this value is outside the range of -1 to +1, then your calculator is going to give you an error because there's no solution. But of course, -1/5 is within the sort of standard range of sine, so we are going to get an answer from this. And right off the top of my head, because you know I can do this, I know my whole sine tables in my head. The inverse sine of -1/5 is equal to -0.2014. Now, remember, our calculator is a tool. Our calculator is not the end-all, be-all. This angle measure is not within my domain, not within the restricted domain that I'm looking to, or interval that I'm looking to work this problem in. So I have to think a little bit, right? This is a negative ratio. Y over r. Remember, you put the sides of a triangle into your inverse trig function. So where is the sine function negative? Well, sine's y over r, right? So when you start at the rotation, the first rotation of 0, whether it's 0 radians or 0 degrees, you rotate pi over 2, that's quadrant 1, pi, quadrant 2. If you're in quadrant 1 to 2, your y values are positive, you're above the x-axis. So I need a couple of angle measures that land me in the quadrants where the sine is negative. So this is basically my reference angle. Don't forget, inverse sine from your calculator is going to give you answers between -pi/2 and +pi/2, or -90 to +90. So this is in quadrant 4, but it's not within our domain or our restricted intervals. So, and I'll have to erase this board to finish the example. But for our quadrant 3 angle, let's see. This is my reference angle, right? So I want to rotate over to pi, and then keep rotating a little bit more. Rotate 0.2014 radians into quadrant 3. So I'm going to have pi plus 0.2014, and I'll write that answer down in a second off my paper. And our angle in quadrant 4 that we're going to be using, quadrant 4. Well, I'm going to rotate through 1, through 2, through quadrant 3, and don't forget reference angles, which is what this basically is, are the number of degrees between the x-axis and the terminal side, not the y-axis. So we're going to go to 2 pi and then back up to get me in quadrant 4. I don't want to be in quadrant 1. So 6 pi, or excuse me, well, I'm thinking of a number. 2 pi, or 6.28, minus 0.2014 means that the x's that I'm actually going to work with in the problem, my critical values, are 3.343 and 6.082. But I'm already sort of taking up my whole chalkboard here, so I'm going to erase this scratch work and just put my critical values over there so I have some more room to work. So here's my critical values again. And I've used them to set up our test intervals. And if I take a value of 1, 2, 3, 3.1, and I plug them into our first derivative, I'm going to get a positive value. Make sure your calculator's in radian mode if you've done your problem in radian mode, which we really should be doing. Then when I plug in a value anywhere between 3.3 and, 4.3 and 6.082, like maybe 4 or 5, just to be it easy, this is my first derivative is going to come out to be negative. And then finally, if I plug in maybe like 6.1 into, again, my first derivative, I'm going to, again, get a positive answer. Yes, okay. So, actually, this should be 2 pi, just to be exact with my interval that was defined in the beginning of the problem. And again, these functions are continuous everywhere, so I don't have any issues with any discontinuities. So when this function, or when this first derivative switches between positive and negative, that means I'm going to have a relative maximum at, well, let's see, I'm going to take the value of 3.343 and plug that into my original function, and get 3.343, comma, 8.24. And we switch from our first derivative being negative to positive, falling and rising again, so we have a relative minimum at, drum roll please, 6.082, comma, 1.18. And that is the end of our last algebraic example. I just got one more that's going to be purely visual, looking at the comparison between an original function and its first derivative, and identify again the idea of critical values, increasing, decreasing, and so on. Thank you very much for watching. Bam! Last example. So we have this crazy function f drawn in white. I want to come up with what seems like would be a good plausible sketch of what the first derivative would maybe look like. Well, so I'm going to look through here and I'm going to try and find out all the places where the original function has a slope of 0 or a slope which is undefined. Because if the slope of the original function is 0, that's going to be a critical value, right, for the first derivative. So it looks like we have a critical value here where the original function has a slope of 0, and it kind of levels off here at x equals 2, and stops bottoming out, and hopefully my drawing is kind of okay for you guys here. Seems like we have a slope here for our original function at 5, and if it's not really 5, I'm going to kind of just cheat and say it is. And then we have, it starts to rise and fall at the x value of 6. Okay, let's try and draw what could be our first derivative. Now our first derivative, our original function is rising. Now if our first function, our function f is rising, that means the slope of that function is positive, and the first derivative gives us, as answers of y, slope. First derivative describes the slope of the original function f. So if our slope is positive, the first derivative is giving positive answers, thus it's going to be over the y-axis. And then it's going to cross through the y-axis here at an x value of -1. So very, very positive, very steep positive slope for the original function. So maybe it's coming through here like this, and our first derivative is crossing through the x-axis at this value of -1, where the original function has a slope of 0. Well, now the original function has a slope which is starting to fall, so it's negative. And it seems like about right here, the original function has a slope that's going to get about as negative as it's going to get, or as small as it's going to get. So I'm going to let this sketch of what could be a first derivative get to its lowest value and reflect that lowest value of slope right here, and then the graph is still, the original function is still decreasing, still has a negative slope, but it's not as negative. So the value of the slope is actually starting to increase, even though it's still negative, until it gets back to a value of 0. So this orange graph is going to come up here and, well, it's going to touch here at x equals 2. But then after the slope starts to increase, still negative, but increasing until it gets to 0, it starts to drop again. So from here to here, this original function is falling, which means all my slopes are negative except for maybe here where it's equal to 0. So I need to keep this first derivative below the x-axis. So I'm going to come up here and touch the value of 2. And again, try and get that deepest part of the bend somewhere underneath where it looks like the original function has its most negative slope, and then it starts to fall off again, and it seems to have the most negative slope somewhere around in here, and then it reaches 0 again as it starts to rise. And so I'm going to go ahead and let my first derivative show its most negative slope value around that interval, and then start to approach 0 again. Maybe it looks something like that. And now this time, at this critical value, the graph actually starts to rise, so the derivative, the first derivative describing that slope, positive slope, first derivative therefore has to give positive values, meaning it is above the x-axis, until we get to the next critical value of 0. So we have a first derivative of 0 here, a first derivative of 0 here. but that slope between 5 and 6 is positive, so that first derivative is above the x-axis, and then it starts to fall again. So I think this seems like a pretty reasonable sketch of what f prime looks like. And again, our critical values here at -2, 5, and 6 means that, let's see, from -infinity up until -1, our first derivative is negative. So again, that is decreasing. Just for one last summary, between -1 and 2, f prime is, let's see, I forgot to write this was positive. And then between -1 and 2, f prime is negative. So that function is, excuse me, the first derivative is positive, the function is increasing. Then it's decreasing from a value of 2 to 5. Our first derivative, again, is still below the x-axis, so we are, again, decreasing. And since our derivatives went from negative to stayed negative, we do not have, again, a relative min or max at the x value of 2. And then from 5 to 6, our first derivative is positive, indicating our original function, even though we could see it in the original drawing, was increasing. And then from 6 to infinity, we went back to the first derivative being negative, and again we could see that function was decreasing. So, man, that was a lot. I hope it helped you completely understand the first derivative, how it shows the function being increasing, decreasing, or constant on intervals, and also the first derivative test, helping you to identify relative max and mins in these functions. I'm Mr. Tarrou. Bam! Woo! I'm ready for a break. Maybe you could take one too, and then go do your homework.